All right, on to section 11.8, power series. So a power series is an infinite series in one of these two forms, where we have a series c sub n times x to the n, or c sub n times x minus a to the n. So these are actually infinite polynomials. We call the c sub n's the coefficients of the series, and for each fixed value of x, the series is a series of constants. So when we actually plug x's into these, then we actually have we have a series of constants that we could look at for convergence or divergence. Okay? So the series is actually a function that is a polynomial. So this series is a function that is a polynomial, and we can look at the domain of this function, and we can think about what is that domain. The domain is the value of x's for which the series will actually converge. Okay, so we have a couple of other little notes here that I've listed out about power series, but we'll keep reiterating these as we go through some examples. So let's just look at a really quick example of a power series. So here is our very first simple example of a power series, just x to the n from n equals 0 to infinity. So what does that look like when we expand it out? Well, that would be 1 plus x. Let's get in closer. So x plus x squared plus x cubed plus x to the fourth plus, and on it goes. So this is an infinite polynomial. But notice that this is actually exactly, right, there's a common ratio here of x each time we're going up by a power of x. So this is a geometric series where the common ratio is actually equal to x. But we also know that this guy must converge, since it's geometric, this must converge for values of x that are between -1 and 1, or for values of the radius, when the absolute value of the radius, which is the absolute value of x, is less than 1. So if we're actually thinking about, like, where does this converge? Well, we can think about values of x. We're thinking of this. This is an infinite polynomial, so we're actually thinking about this as a polynomial, and this is going to converge for values of x between -1 and +1. So this is going to converge for values of x that are in between -1 and 1. So there's our first power series. So we'll come back, we're going to look a little more at that too. We're going to get a couple more definitions, but I want to look at one more power series. So here is another power series. So this power series has an x minus 3. We say that when we have it off-centered, when we have a power series of the form c sub n times x minus a to the nth, we say that that power series is centered at a. So we say it's centered at x equals a. So this particular series we would say is centered at x equals pi over 3. So we'd say it's centered at x equals pi over 3. A way to think of that, like we did on that last one when we drew the x-axis, the way to think of that is you could think of pi over 3 here on the x-axis, on a x on a number line for x, and we could say, okay, so this is a polynomial that is centered at x equals pi over 3. We can think about that. Okay, so what does this look like if we actually were to expand this guy out? So if we were to expand this power series out and look at what does that infinite polynomial actually look like, this power series, as we go and we expand it out and we think about, okay, well, what would it be at n equals 1? So if I start to expand this out at n equals 1, I would have 1 over 1 factorial times x minus pi over 3 to the first. And then I would actually have a negative, the next term, when n equals, get that all on the screen, when n equals 2. It's got a switch on it, so I would have a -1 over 3 factorial times x minus pi over 3 to the third. And then the next term, when n equals 3, as I go to expand this out, is going to be a +1 over 5 factorial times x minus pi over 3 to the fifth. So we notice on this particular one, the pattern that we're starting to see here, right? We see that factorial and that power match, but we've got odd powers, odd factorials, we've got a switch, and this goes on and on and on. Okay, So there are two quick examples of power series. This one, we don't know where this is going to actually converge for. This is not a geometric series, and so we'd have to think about like, well, where does this converge? And that brings us to our next piece, which is when we look at a power series. Here's that same example. When we look at a power series, what we want to know is, where is it going to converge? Where is it going to diverge? We want to think about, this is the key here. When we look at a power series, we really want to know, what is the set of the possible inputs, which is the set of all the x values that the series actually converges for. So what x's can we plug into these series so that we get back an infinite series that converges? So we want to find the domain, the set of possible inputs for these power series. Okay? So we're thinking these power series are functions. Anytime we have a function, we got to know, what are the possible values I can plug into that function? What is the domain of that function? Okay, and that gives us this theorem called the theorem about radius and interval of convergence. And there's a lot here, but we're going to work through this with some examples. So let me read it out, and then we'll go back to some examples. So a power series, again, is a series C sub n x minus a to the nth. I did not, at this particular one, I didn't write the possibility that when we are centered at 0, at a equals 0, that the power series looks just like C sub n x to the n. I didn't write that out for this one, but we also have that statement, that if it is centered at 0 instead of centered at a, we don't have the x minus a, or you just plug in 0 for a. Okay, so when we have a power series, we have three possibilities. We have the possibility that the series converges only at x equals a. So for just a single value, this is a single value convergence. This is the most restrictive type of convergence. It only converges at a single value. Only converges at a single value. Now, every power series that we look at will at least converge at a. It has to converge at just a, because if I plug in a into this polynomial, if you just look back up here at this polynomial, if I were to plug a into this polynomial, it would zero out all those terms and leave me just with the c naught, or the constant. Okay. The other possibility, of course, is that it converges for all values of x. So if it converges for all values of x, for all x's, this means it converges across the entire number line. And we actually have what's called an interval of convergence from negative infinity to infinity. It converges for all possible values of x, versus the one above where it's converging only at a. So this converges everywhere. Okay? This converges for all values of x. Okay? It doesn't matter, we can plug any x in. So then we get what's called a radius of convergence of infinity and an interval of convergence from negative infinity to infinity. The one above that was most restrictive, we actually have a radius of convergence of 0 and only converging at that single value. Okay, so if we're actually thinking about a number line and we're thinking about having a power series, so when we talk about a power series, I'll come back to that last one. When I'm talking about a power series, any power series, C sub n times x minus a to the nth from n equals 0 to infinity. Anytime we think about a power series, when we're thinking about what's the domain or the set of x's, set of x values for which this series converges, it's always going to be around some specific point, a. So we've got a couple of possibilities. So for which values does this converge? Where along this number line for x does this converge? And so we've got a couple of possibilities. The first possibility is where what we call the radius is equal to 0. So if the radius of convergence equals 0. If the radius, that's our first possibility. That means that there's only a single value. That's the most restrictive type of convergence. So if the radius equals 0, that means that we converge only at this single point, that we have no radius. We don't go anywhere. We can't go to the left or the right of this point. We only converge when x equals a. Okay? So only at x equals a. And this gives us what's called an interval of convergence that is literally, it's not even an interval. We call it an interval of convergence, but it is only at a. And now the second possibility that we've discussed is the opposite, the other extreme. So the other possibility is that we actually converge everywhere, that we can plug any value of x in and we will always have convergence. So here's our A point, but turns out that we can actually go across the entire number line, right? Giving us, this means all values of x. So that's our other possibility. So all values of x. This gives us what's called a radius of convergence that is infinite. So we can plug any x into a power series that has a radius of convergence that's infinity. It doesn't matter what we plug in for x, we will always have a convergent series. And this gives us, on this one, an interval of convergence. Rather than just a single point, it gives us an interval of convergence that goes across the entire number line of x, from negative infinity to infinity. Okay, then we have a third possibility. Okay, so a third possibility. And a third possibility here is if there's a single positive number, we call it r for radius. We've been talking about this radius. But our third possibility is that there is a positive value r, and the series only converges when x minus a is less than r in absolute value, and it diverges otherwise. And that is what we call the radius of convergence. And then the interval of convergence is actually going to take one of 4 different forms. So it could be that it is an entirely open interval, or entirely closed interval, or half open, or half closed. So let's look at what that looks like. So if we have a power series, that has a finite radius, okay, so a finite radius. Oops, got the wrong tool here. So what if we have a power series that has a finite radius? So what if we have a finite radius of convergence? Okay. So r equals some finite value. So what that's going to mean is that we have some values of x. So here's our A where we're centered at, and that means that we can actually go to the right r, a distance of r units, and we can go to the left a distance of r units. Okay? The radius, meaning we can go back and forth, which puts us at this point right here becomes a plus r, and this point to the left becomes a minus r. So back to that definition, what we're saying is that x lies somewhere in that interval. So we say that the absolute value of x minus a is less than r. Now, what happens at the endpoints we can't actually put on this number line. So what happens at the endpoints, it can vary. So endpoints might be included in the domain, included or not. Okay, so that gets into where we actually have to look specifically at those endpoints. So then we have some possibilities. So the interval of convergence has, again, the 4 possibilities. So we have 4 possibilities. So the interval of convergence has 4 possibilities. It is either a minus r to a plus r, open, closed, where both endpoints are included, or half open and half closed. Okay? So one of those possibilities occurs at the endpoints. So the interval of convergence is one of those. So the endpoints might be included or not. We have to think about what happens at the endpoints. We have to specifically look at what happens at the endpoints. Okay, so that's how we're going to find the domain. We're going to actually look at our series and we're going to say, well, for what values of x would this actually converge? And before I end this video, I just want to go back to that very first example we did, and I want to talk about what would be the radius of convergence and what would be the interval of convergence. So let's go back just to that very first example that we had looked at right up here, because this was one we're familiar with. This was a geometric series, and we'd already talked about if it's a geometric series, it's going to converge when that common ratio is less than 1. So we'd already looked at this. We even had drawn the graph and we had said, oh, this is going to converge. It's centered at 0. Okay? So this is definitely centered at 0 because we could have, we don't write this, but we could have written it like that. That means my A value is 0, so it's centered as a power series. And in the verbiage and the language of a power series, that means it's centered at x equals 0. Okay? And so here's my x equals 0, and we already know that the ratio in a geometric series has to be less than 1 to get convergence. So we actually already even drew this in. We came in here and said, okay, here's where we're centered at, here's my A, and if the absolute value of x has to be less than 1, that means I can go to the right 1 unit and I can go to the left 1 unit. So in the language of what we've just talked about, for this particular power series, we would actually say that the radius equals 1, and the interval of convergence is equal to -1 to 1. What that means, that is what we actually think of as the domain of this power series. This is the values of x for which this particular power series, this infinite polynomial, will converge. So this is the domain of the power series. When we think of it in function form, when we think of it in terms of this like infinite polynomial. So, you know, we're connecting a lot of what we do with polynomials now to infinite series. So we're looking at infinite polynomials and we're saying, okay, so if I had an infinite polynomial and I can connect it back to all the stuff I just did with the infinite series, where are these now infinite polynomials going to converge? What is their domain? We call that the interval of convergence, and liken it to a radius because we're always centered around a specific point. Okay, so that's the intro to power series, and we'll come back in the next video and do several examples of just more power series and where do they converge and what are those radiuses and intervals of convergence, and a process for coming up with those.